Here's one of my maybe all-time favorite examples of morphogenetic problem solving. This is what you're looking at here is a cross section through a kidney tubule, and it has a space in the middle. And normally what happens is that 8 or 9 of these little cells get together and they work together and they build this tubule. But what you can do is you can make newts with extra genetic material. And the first amazing thing is that you still get a normal newt, even though you have multiple copies of the chromosomes. That's already amazing. But what happens is the cells get bigger to accommodate the extra copies of the genomes. And as the cells get bigger, it turns out that fewer and fewer of them will work together to make exactly the same size lumen. So that's amazing thing number 2. They scale their collective behavior to the size of the cells. But here's the most amazing part. If you make the cells truly gigantic, and I believe this is either 6 or 8 times the normal DNA that they should have, these gigantic cells will now just wrap around themselves, not work with anybody else, but wrap around themselves and produce and leave a hole in the middle that's the same lumen. So now here's why this is incredible. It's because this is a completely different mechanism than this. This is cell-to-cell communication and standard tubulogenesis. This is cytoskeletal bending. And what you're seeing here is a kind of top-down causation. It's the ability of the system to call up different molecular mechanisms to achieve the same large-scale anatomical goal. Getting to, so this is, remember James's definition now, the ability to get to the same outcome, the same region of anatomical morphospace by different means, by using different tools in your toolkit to get this accomplished. Now, just think about what this means for biology. If you're a salamander coming into this world, it means that you can't rely on, you don't know how many copies of your genetic material you're going to have. You can't rely on the size or the number of your cells. You don't know any of that. You have to figure out all of these things from scratch. And you have to be able to make a proper salamander of the exact same size, even if you can't rely on your own parts. Not only weird perturbations from outside, like somebody cuts an embryo in half or some sort of damage. This is much more fundamental. Even your parts are unreliable, and you still have to be able to get the job done. So there are huge evolutionary implications of this, which I don't have really time to go into now, except to say that this kind of plasticity, the fact that evolution gives rise to problem-solving machines, not specific solutions to specific problems, has major implications for evolution itself. So there's this constant feedback loop between the intelligence that's evolved, that's due to evolved mechanisms, and the feedback on the evolutionary process of the fact that your parts can make up for problems, the fact that even damage, various kinds of damage, you still get a workable animal.